Before we begin, let me read this ACM SIGGRAPH policy against harassment. This live stream is moderated by ACM SIGGRAPH. We ask that all comments stay respectful of others and respect ACM's policy against harassment. This means to exercise consideration and respect in your speech and actions, refrain from demeaning, discriminatory, or harassing behavior and speech, and be mindful of your fellow participants. All right, so let's begin. And I've disabled my green screen today, so we won't run into performance issues, hopefully. I think the streaming and shader toy, they fight for my GPU, and I have a small little laptop that is struggling. So let's hope things stay good today. And we will dive into the course right away. We don't have a guest today, so we can cover a lot of ground and get into some exciting stuff. So this is class 5. We have been on a journey to kind of not just implement a ray tracer blindly, but try to understand some of the principles behind it, and without going into too much of the math, and just understanding what things are, how lights and materials interact, and how images are formed, and we're building it up slowly. So the ray tracer we've written so far, not the most efficient, but I wanted to write it in a way where it's incremental. So every class we had a few lines of code, and we get to see some results of a specific part that we want to focus on each class. So far, we've done a lot already. So we kind of established like how images are formed with the interaction of light with the material, and as the light from the material then reaches our eye, we see those materials or objects, and a lot of things are the property of the material themselves, but things are also dependent on the viewing angle and the angle of the object with the eye. So there's like many factors that go into the final image that is formed into a retina. So we try to model that as best as we could. And so far we've seen some good results, and we started out with one sphere, and we added some more, and we figured out how to intersect rays with spheres, and we tried to get a simple lighting model going where we first put the light at the eye, and then we did the cosine angle with the normal to kind of figure out how much of the light should fall on the object based on the shape of the object, because the normals for the sphere are essentially very easy to calculate, and we did that. Then last time we talked to Brent about materials and BRDF. So materials, as you know, they come in all forms, and there are properties of materials that affect greatly how light comes off of them. So there are ways to model that, and one of the common ways is to model them using something called a BRDF, or a bidirectional reflectance distribution functions. There are other forms of modeling. They're based on BRDF, and you can get into more complexity. But today what we'll do is we'll try to see if we can implement simple BRDFs and how to incorporate that. So far we've been doing pretty ad hoc material, because our material was essentially diffuse. So let's see if we can get to that today. So no gas, we'll do some recap, and then talk about reflections, and then go on to the second part of BRDF, which is actually implementing it. The BRDF implementation is a little bit tricky, but when it comes together, then you won't need ad hoc methods. So you can rely on the BRDF to give you properties of the material that you need, and then you can accordingly then continue on rendering the object. So where to find the files on the Google Drive? This presentation is available as a PDF on the drive, and the shaders today, there are 2 shaders I'm sharing. They are available on my profile as well. So if you want to follow along, just grab those shaders, fork them, or make a copy, or whatever you want to do. So let's get to it. So far, any questions on the things we have covered so far? let me go back to the thing. Yeah, so if you have any questions at this point, let me know. So, all right, so wait for a couple of minutes. Let me drink some coffee and then we can continue on. All right, so excellent. So then we can continue to progress. Going back to the presentation. So just to recap the math a little bit, because math will get complex. Just I want you to make sure that you're following along. We figured out how to put a light in the scene, and we're treating our object as diffuse or Lambertian because they are not view dependent, and we figured out that we can take the normal at the point of intersection, and then the angle is what we would use to kind of graduate the color. So that gives the diffuse lighting effect. As the light goes away from the object, you get darker areas, and as the light shines on the object, right, then the normal is essentially parallel to the direction from the light, which means the object is in full light. So we represented that as a graphic which looks like this. So we'll use this kind of graphic to kind of define our material. So when you look at this kind of graphic, you'll immediately know that we're talking about a Lambertian surface or diffuse material because the light is kind of going in all directions. So, and then we also talked about textures, that the material itself can have a color, a sphere can have a color, or it doesn't need to be the same color all over the material. You can have varying material. So texture is a great example of a varying material because the base color then changes from point to point based on the texture coordinates. So you can similarly think of like your material may not be a blue ball, but maybe using some equation, something you can have varying properties along the material. So if you can have varying properties, you can have textures representing those properties where you can, instead of mapping color, you can map properties. So if your properties were floating point numbers, then at each pixel, they would be some property that you can map to. So then you establish the material as it has some color, and that color can vary along the surface of the material. So that we'll call that the base color. So when you go to the other extreme from the diffuse Lambertian surface, you get a perfect mirror-like surface. So where the light is going out only in one direction, and that direction is mirrored along the normal at the point of intersection. So the dark black color, the light is coming in, and the gray arrow is the direction that it is going out, and it is mirrored around the normal at the point of intersection. So that's how we would implement a mirror object, and that makes sense because in a perfectly reflective, you look in the mirror, that's how images are formed. They get laterally inverted, but they are bouncing at a very symmetrical angle to where they come in. And if it's like if you take a mirror and kind of like take some and then kind of smudge it, you won't have perfect mirror, so it might look something like this. So using diagrams like this, you can kind of like start describing properties of material. So this is still a reflective surface, but not as reflective as the mirror. So you may be able to see some things, but they may be blurred because it's going in many directions. So going from one extreme of totally diffuse, totally reflective, to something more on the reflective side, less on the diffuse side, you can imagine there may be different materials behave differently. So for every single material that you have in your scene, you may have a different looking diagram that you can come up with like this. So in reality, we talked about that things are even more complex than that, because in a glass-like object, rays can pass through, and you have transmission of some kind, and these things obey the Snell's law of refraction. So ray comes in, refracts a little bit, and goes out on the other side. And it may go out, if it's a nice glass-like object, it will go out. If it is like semi-glass, like a diffuse plasticky like thing that is transparent, then it may go out in different directions. If it is a subsurface thing, then the ray might jump around here and then may go out in different directions as well. So sometimes you'll see that if you shine a light onto your skin, you'll see the way it lights up is because of that subsurface effect, because light is going into the skin, but then going around inside a little bit through your skin and then coming out of some other side. So and then taking on the color of the blood. Sometimes if you, as a kid, if you have done this, put a small flashlight into your mouth and turn it on and blow your cheeks out, you'll see this reddish tinge that the light looks like. So there's complex behavior of light with different materials. So we could, in effect, start modeling these objects and different materials. So in a simple case, it was like this. But say you have different materials, it may be different kinds of these lobes, as we would call them. Not only that, but an object can have different kinds of materials on it, or it can be made up of some kind of a composite thing where a metal sphere, for example, is rusted in the spots, and then you have this mixture of two kinds of materials all over the place. So, so things can get complicated, and we could basically take each material and ask more questions of it and exactly model it, but it helps to kind of like simplify things a little bit. So we'll do that in a minute. And before we do that, let's talk a little bit more about reflection. So, because we're going to implement that today. So as I showed you the kind of the diagram for mirror, the rays go out only in one direction, reflected evenly about the normal. So if we do the math of what is happening, so our material is a sphere, which is, again, this curve here that represents the sphere. So this is the ray that is coming in. This is the ray that is going out. And what we are trying to find out is how should we represent the reflected ray. So we want to symmetrically reflect about the normal. So if you work out the math, it comes out to be a simple equation like this for the case of sphere. All you have to do is take the dot product of the incoming angle or incoming vector, and then with the normal, and then do the simple math. So that will give you the reflected ray direction, and then which we can use. So what we would do then is like shoot a ray. If it hits an object and it is a reflective material, we would shoot another ray now. Because in the past, what we had done is we had just stopped at the first object. We want to capture the reflection, so we are going to shoot a ray from the point of intersection into the direction of the reflected ray. So this is what we'll do. So we this from the eye, we shoot a ray. It hits the sphere. If it hits the sphere, and if it is reflective material, we are going to compute the reflected ray, which is given by this equation. And we would then shoot another ray, not from the origin, this point, as we have been doing, but from this point into another direction. So then it might go and hit another sphere. And we'll do the same thing. We'll reflect it again, and it might hit another sphere. So we keep doing that until it doesn't hit the sphere. It just goes into darkness void where it's not hitting any parts of the scene. And at that point, we would assign the color of whatever came out to this point. So imagine like this point is taking on the color of what is coming from here, plus what is coming from this other side, plus what is coming from the outside. So it's like a combination of what it hits, and that's how you get reflection. And it can get complicated because if you have a lot of objects, they're all mirrors, you can get this infinite ray bouncing all around, and it never stops. And you can set some threshold for how many times you want to bounce around, and then find the final color that way. Otherwise, you'll be in this infinite loop of bouncing around things. So that's what most renders do. They set a fixed bounce depth, like how many times you want to bounce, and they do those calculations based on that. So let's try that. Go into the shader toy. And so this is already implemented, but I'll go over it step by step, because things are getting a little bit more complex in terms of code, but it's still additive code. And all I have done is some refactorization. So this code remains the same. And intersection of the ray with the sphere, we haven't changed that at all. So, and what I have here is, again, our 4 spheres with different colors in different positions, and 1 light. So let's figure out what we did different here. So first thing we do, so this, again, the main loop, which is called for every pixel in this on the screen. And we make our scene. And we're not animating it, even though we're passing the frame. So make scene is essentially just creating these spheres and setting their properties, putting them in different places with different colors, and setting up the light. So next step would be to then, what we did before, again, this part has not changed at all. So what we're doing is just some transformations to make sure our coordinate system is set up in such a way so that it goes from -1 to 1 from left to right, -1 to 1 from bottom to top, and we are sitting at the origin, viewing outwards towards the negative z-axis. That's our camera setup. So you can have any camera setup you want, and ideally you want a more flexible camera system so you can move it around. So that's what interactive applications do, but we are not doing that because it's something you can try, but it just adds complexity to the code. We'll just set the camera at this particular location where it's easier to compute things. And so next step, what we're going to do is, because we want to take more than 1 sample per pixel, we are going to take a pixel and then find a random perturbation to that ray, so that it stays within that pixel, but it's in a little bit of a random direction. So that way, next time around, we get some other random direction. And then if you do multiple samples, they will all be within that same pixel, but multiple of those samples in random directions. So that gives us a nice anti-aliasing effect, and that we can see at the edges. Now it's nice and clean. Next thing we did was adjust for the aspect ratio. That's normal. Otherwise, things would be squished in one direction or the other. So you could flip it, and it should still be fine. It would instead squish in the horizontal direction. So next, we set up our ray. So remember that we are sitting at the origin. That's where our ray starts from. And then we're going to set a ray direction that is going through the pixel. At the screen depth, we are setting the screen up at some screen depth, which is probably -2, I think. So next thing, and this is where things start changing. So we are going to do 100 bounces at the max. And if things don't converge by 100 bounces, we are going to give up. And that's totally fine. So for each of those bounces, we are going to try to intersect with all the objects. So we send out the ray. First, remember, we start from the origin, send out the ray, and try to intersect all objects. So what I did was I took the intersect sphere code and then I put it up so that we can call this in a loop. So this is for every bounce we are going to traverse the scene again. So you can now see that that the computations are multiplied 100 times because we are now bouncing. So we're doing per pixel and then multiple samples per pixel and then multiple bounces per ray. So you just multiply all those, and that's the number of times things are getting computed. So if we find an intersection, and we'll find that the sphere that got intersected, the index of it, and find the intersection parameter t, which we'll use to calculate the hit point. So ignore this part of the code because it's just some quirk of shader toy that I couldn't figure out. So it wants I sphere to be constant of some kind. Anyway, so once we find the intersection, we find the hit point where we hit the ray with the object. And at the hit point, you want to find the normal. And you find the normal. And this may be just repeated code, so you probably don't need this line. So then what we do is we reflect the ray at the hit point. So if you look at this code, I found the normal, and then using the normal and the ray direction that was coming in, I just use the equation I showed you for reflection. So this is the reflected direction. So ray hits some object, it is then reflected evenly about the normal. And now we are going to start another ray. And for that ray, and the origin is going to be the hit point, and the direction is going to be the reflected direction we just computed. So that's it. So that's just 3 lines of code are going to create unlimited reflections for us. And so we're not going to have any color because these are like essentially mirrors now. So instead of setting the color here, what we are saying is when the ray goes out into like a no man's land where it's not intersecting anything, at that point we are just going to use the background color. And the background color, what I did was I modulated using the height or the y direction of the ray. So you get this gradient here, and the same gradient is reflected back into the sphere, but now it is also using the geometry of the spheres that it is seeing. So that's why you see things get reflected in a way like that. But there's only color it's using is from the background. So you can see the reflected spheres here, and we can try different things here. Let's see what happens if we just use like 10 bounces. So it's still good. And if we use only 1 bounce, so you don't get anything because now it's like it's just stopping wherever the first thing is hit. So things are getting dark. So 2 get some reflection, but it's dark because we gave up after 2, so this color comes out to be essentially black. So as we keep increasing the number of bounces, you start seeing reflections and better color for the reflections as well. So I think in some cases you may have you can try with 1,000 bounces and see what happens. So it's like seems like there is some number after which you don't get any benefit. So many renderers will kind of give up and say, oh, we don't need any more bounces than that, and that's where we'll stop, because the computing is exponentially multiplied by the number of bounces. So that is reflections. Any questions on this so far? Let me go back to the... All right. Any questions? All right, so I'll read some. Somebody had a question about, are all the spheres reflective? Yes, so they're all basically reflective. They're essentially reflecting everything. So with the white or the black spotting places where the ray tracing has not reached. So the black spotting is the place where the ray has not reached. And the whites are basically just reflections of the object. So it's actually hard to see. If you've ever been in a mirror house of sorts where things are infinitely reflected, it is hard to tell what is going on, because things are getting reflected. So you don't know, like, where is this sphere coming from? I don't know if you can trace it, what this reflection is. Is it a reflection of this sphere or something here? And so things are hard to it's hard to figure out where everything is reflective. So as we go along, we'll make other kinds of materials where we can put together some reflective ones and some diffuse ones, so you can actually see what is going on. But in a perfectly mirrored area, it is pretty hard to tell what exactly is going on. Could a renderer dynamically compute the number of bounces? It's hard, because we don't know, like, how the objects are placed. It could be, like, for example, the objects when they are very close to each other, and you could just be bouncing around between them and not gain anything more. So I think it's just a thing that people set when running their scene and try different values. There's, like, similar to the samples per pixel, like what kind of results can you get away with the minimum bounces and minimum samples per pixel. So that's really on the user side of things, where it's an open setting where you can try these things out. So could you stop bouncing earlier if you hit a light source? If you have a mixed kind of setup where you have light sources and other materials, then there are different ways of handling these kinds of things where you can achieve more. You can purposely send rays to the lights instead of to the other objects, because that's what matters most, is where the lights are, and then if the light is hitting the object or not. So we'll cover some of that, where we'll shoot more rays towards the light, and that's where you want to get most of your information from. What are the number of bounces used in real time versus offline? Well, it all depends. I think this is an open setting on the user side. So in terms of how renders in VFX work, they are trying to create a final frame. They'll set a high bounce for the final frame. If they're just trying to get a preview render, they'll set it up to a lower value. But again, it's just an experimentation. And then in reality, you would not have this kind of perfectly mirrored surfaces. So you wouldn't lose that many rays to just like constantly bouncing. So I think you can do further optimizations in that area. All right. So that's good. So this looks pretty cool, actually. So again, even like I can't tell like what am I looking at, like especially with one of the spheres here. Like, is it a sphere that is reflecting, or is it a reflection of a reflection? It's pretty crazy. Okay, so let's go back to the code. So any questions about the code? So again, we're not doing anything fancy here. Like, main difference is this reflected direction, and then redefining the ray to be not from the origin. So that's why to take the ray definition out of the main loop. Other than that, it's pretty much the same code. Okay, so that's done. Like, getting back to the mirrors. So now we're done with two kinds of things. So that's pretty cool. One extreme was the fully diffuse, and the second extreme was fully mirror. So now all we have to do is things in between, and those are hard. So that's where we get to the actual BRDF. So as I said, like, we could take each material, like this yellow paper or red paper or some cloth or other fabric or canvas, and then create BRDF for that or specific properties and figure out how to reflect rays for that. But that gets cumbersome. So what we could do, and what Brent described last time, is come up with some properties that you think are common to everyday objects, things that you might model, and that should cover variety of materials. And that's what BRDF tries to do, is try to kind of get an understanding of what different materials might be, and using few properties, you should be able to create a variety of materials. So that way you don't have to kind of figure out, like, there are machines that you can get that will try to approximate the BRDF. So you take a material, a swatch of some kind or an actual object, you put it in this machine, and what it does is it rotates the object. There are lights inside. It rotates the light and takes pictures from every possible angle of the light rotation, every possible angle of the object rotation and combination thereof. And it tries to figure out the BRDF or a lobe like this for that object. And that can be cumbersome, but people have done that for research purposes and for documenting BRDFs of interesting materials. And one of the early data was available from Mitsubishi Research Labs. It's called the Merle BRDF data. And that's what Brent used some of that to kind of figure out what they are. And not only that, but he looked at existing research, and then also by taking, like, we could then, after capturing these materials, you could essentially create a giant table. Like, if it is this, then do this. If it is this, then do this. But that gets cumbersome as well. So what Brent tried to do was to find equations that would fit the data. And I saw him kind of work for weeks on this with Mathematica, trying to fit some data, trying to create curves and for different values. And not only that, but he wanted to create properties which were usable by artists, or usable by artists by using vocabulary that they understand, that they want to use for materials. And on top of that, they also want to have nice ranges. So when you're working with things normally and that are physical, the units may go from one range to a different range. So the good thing about the Disney BRDF is that most of the properties, or actually almost all, they are nicely in the range from 0 to 1. So you can create sliders for the artist, and they can tweak them around until you get the material that you want. And because these properties are from 0 to 1, you can also make textures. Instead of specifying a constant property, you can have a property that is varying over the surface. So some of those properties that are defined through BRDF usually, and again, this is not the BRDF, so we don't need these specific properties, but they are the ones usually used to kind of specify a material. And under the hood, you do some calculations and try to figure out the actual BRDF using these properties. So again, these properties are exposed purely as a convenience to the artist, so that you can set up your material properly, and then you do all the complex calculations, taking these as input. So base color is, we talked about it. Base color is the inherent color of the object, and that is a vector, usually red color or blue or whatever, but it can also be surface varying. You can have a texture, you could manipulate or modulate in many other ways. And then you have such of other properties which can be thought of as floating point numbers, like ranging from 0 to 1, like how metallic you want something to be, how rough you want it to be, how specular you want it to be. So specularity is like when you shine a light on it, it's one of the reflective things, like how reflective it is. You get this specular highlight is what it's called. It's a shiny little light on metals and other shiny objects. And another property which I haven't seen used in other BRDFs, it's part of the Disney BRDFs, is the clear coat, which gives you like a new car-like shiny coating, like a billiards ball, or again, a car hood or something clean and nice and plain paint. And sheen is something that you would see. This is again, you see it in more of the cloth-like objects. There is like certain shininess to it, but it's not a metallic object. So, and then there is this anisotropicness to it, which is common to all BRDFs, because anisotropic is just a term that means things are view dependent, which means if you change your angle of view, things will look different. And that's like how much of that happens is as part of one of the parameters. So again, they're all related in some way, and they are all used to calculate the final BRDF. So final BRDF is ultimately you can multiply it by the normal at the point of intersection and then find the actual color. So it follows from essentially the equation, something like this. So then the BRDF itself is not enough. You got to do this, and then you got to do other things to actually use it. And but what we can now do is we can specify a material property for the object using parameters, which would be something like this. And then we'll have a function that will calculate the BRDF. And we want to keep that like as a mathematical function that just computes things and then gives you back a BRDF. And the BRDF itself is computed using these three vectors, essentially: the normal, and the incoming angle, and the outgoing angle. So once we compute this, so these three things form like a frame at the tangent where the ray intersects, or tangent to the surface. So we'll have to move a coordinate frame on the surface where all these computations can happen. So usually all the BRDF calculations are done using this particular frame as a reference. So we'll have to do some transformations there. And then they're also all done in linear space. So if your monitor is not, obviously it's not linear, because monitors normally have some gamma to it. So we'll have to gamma correct the results. And then the third thing you normally need to do is something called tone mapping, because all these calculations happen in what you can think of as HDR, or high dynamic range space, where things things can be like the numbers that come out of it may be larger than 1. So you got to tone map it as well. So the tone mapping is a process where you kind of bring it down. So usually you want it's an artistic process where you want um, if you ever seen the Ansel Adams pictures, like he would meticulously make sure that he would have like 4 to 8 f-stops represented in his images. So the darkest of the darks and the whitest of the whites, they are represented, and then some in between he would do this tone mapping process. He would do it in a more physical film burning process, but we can do that in the computer now. And so you want to bring those ranges back and then make sure that they are, because we can only see on the monitors from 0 to 1. So you'll have to bring that back without compressing or without blowing out the highlights or without making everything too dark. So that's tone mapping. So there are other things that you need to do besides just computing the BRDF, computing the angle, finding the color. You'll have to do the tone mapping, and you'll have to do the gamma correction. So that's just normal process for any kind of computer-generated imagery. And one of the things we use in this process is the EXR file format. So the EXR file format is something that can represent values in high dynamic range. So we can preserve that as long as we want until we need to do the final HDR to device space, because each device, so when we make films, it may go out to different devices. It may be streamed, it may be watched in the theaters, it may be on the airplane monitors. So we would cut a film to all these different devices that are possible, and then tone map separately for each of those spaces, so that nothing is lost and they're all optimal for that particular device. Anybody have any questions so far? So on the materials and what needs to be done for calculating the BRDFs and for figuring things out. So let me go back to the... So what kind of samples per pixel do production renders like Hyperion use? So the renderer itself is it's just exposing the samples per pixel, and it is up to the artist to use what they want. And so if you use fewer samples per pixel, you get some idea of what the image might be. So in a preview type of render, they might use low samples per pixel, and get back the image faster and just make quick decisions about the image. And as you progress, you can start increasing the number of samples. So it's an artistic choice for the artist to how many samples per pixels to use. The renderer just exposes that, and with the warning that the more you use, the slower it is going to be. So some of the frames can have up to 256 samples per pixel. And you can imagine that, like for a 2K frame, doing 256 samples per pixel with all the bounces and everything, and that like sometimes some frame might take 2 hours, 3 hours, or 4 hours to render. So that is true. So I think we use the BRDF. That's for all of the materials, and a lot of these materials are complex, and I think they're authored by the artist. Right. So the shader that you write, so shader in terms of what you would call a shader is essentially these set of parameters that are that can be painted, or you can set the properties to some values, and because they are layered like that, imagine like you are trying to, you have a surface and you reach a specific point on it, XYZ, and you're going to ask like, what is the property of this material right here? And you're going to look into your 8 or 10 parameters you have, and you can get some value for that particular position in space for that object. And based on that, you would then sample in the direction that the BRDF is telling you to go look for more light. So um, so it's very generalizable. We can create pretty much any material. So far, we haven't had trouble. You can create different looks as well. You can essentially, it's a shader, right? So you can do whatever you want with it. All right, so let's do some BRDF. So what we're going to do today, in the time we have left, is we'll do it in two parts. Today we'll set up how we would make and use the BRDF, and then in next class we will add some more complex BRDFs to that, and then we'll generalize it a bit. So I don't want you to get lost in the math here because there's going to be a lot of it, but just try to understand the ideas, what we're talking about here. So here it is. It's the shader toy called BRDF-diffuse, and it should be available from my profile. And in it, you're seeing just a sphere. And what we'll do today is implement the diffuse part of Brent's BRDF. So all the code I'm using for the BRDF itself is directly from the website, and I use some other code from the PBRT, the physically based ray tracing book, but it's all available, and it's available here too. So what I wanted to try was to see if I can just get the diffuse part done today, and then we'll add more as we go along and clean up. So again, I wanted to keep most of the code same. So this is going to be same code that we had before. Again, make scene is we're going to simplify things a bit by just having one sphere and one light. And then when we generalize in the next class, you'll see how it all works together. So, but our code is kind of there to handle more lights and more objects, but we'll just use one for now. So same code, traverse, intersect, and find the hit things. So right here is when things start becoming complicated. So now that we find the hit point and the normal at the hit point, we are going to transform everything to that tangent space that I talked about. So we're going to make this coordinate frame at the point of intersection. So then this particular function does that. So we're going to take the hit point to the light vector and hit point to the view vector, and the hit point itself, and get back in tangent space these values. So let's see what it does. And that part is straightforward. Essentially, we are going to create a coordinate frame here and a transformation matrix, and you just multiply them with the transformation matrix. And you get back the light vector, the view vector, and the normal vector in the tangent space. So TS is for tangent space. So this is what the BRDF calculations will use, because that's how normally a BRDF is defined in that space. So So that's all is happening here. So this is all this conversion. So then we'll do some other, it's mostly different dot products for different angles and what the BRDF needs. And I'll cover some of that when we go to other kinds of materials. So let's just do the diffuse BRDF. And it takes like some of the properties that we are defining in the material, like roughness and metallic, and it calculates this diffuse term. So this again comes from Brent's code directly. The calculate diffuse term is somewhere here. So this is again the things that he came up with in his equations. They are physically plausible, correct, and they do the right thing in most cases. So they're all, so I'm not going to cover in detail what they actually do. Just take it for granted that it works and calculates the diffuse term. So, and there's a lot more math here, and that, again, I'm not going to cover because this is like months of work on Brent's part, that some of it is pretty complicated. So just assume that this gets you the BRDF for the diffuse part at least. So once we get that, so we add the specular term to it, and specular term we'll cover in the next class as well. So we're just covering the diffuse for now. And then we get the final color with just multiplying it by the normal to the light angle. And that's it. So the rest of the code remains the same. We again do multiple samples, and then we get this. And then, as you would notice, this is too dark because we are not doing any gamma correction, or we're not doing any tone mapping as well. So let's do that. I think I'll use a trick that PBR uses. It's like we use a simpler version of tone mapping. The tone mapping can be complex, and it's more of an artistic choice. You try some things out. It's automatic tone mapping is hard. Tone mapping, all we'll do is we'll just reduce it a bit so that then the highlights come down a bit, and it should be just fine. And the gamma correction is where things will get brighter. So let's see what it looks like after tone mapping. It might even get darker after tone mapping. So instead of using that, I'll use tone. Okay, it did get darker. So then let's do the gamma correction. So gamma correction, if you look at any kind of display device, it has this profile of where things are not linear, the brightness levels. What we normally do is we have a lookup table. Every facility has a lookup table that calibrate the monitors are calibrated against, and you then kind of remap the colors or the brightness levels for each of those pixels based on that lookup table. It's actually a big deal where we need the monitors to be calibrated perfectly. So there is calibration software, there is color calibrated monitors that you can buy that are twice the price of normal monitors. But that's what like a good facility would use, where you want your users to be working in a fully color corrected environment. So in general, you can approximate that lookup table with a gamma curve, and that's why it's called gamma correction. So that's what we will do. We will figure out a value for the gamma. And usually it's like 2.2 is a well accepted default gamma value. So if you don't know anything, you set your gamma to 2.2 and things should look better on your monitor already. So if your monitor has the facility to set up a gamma, you can just use 2.2 as a good value, and things would look better immediately. So because the gamma is a nonlinear curve, it's a gamma curve, we will do some measurable. So we'll basically just raise each of the values to the power of gamma, 1 over gamma. So that will make it an exponential curve, and each value will be remapped to that. So and then this would change to final color. Let's see what that looks like. There you go. So much better. So so this is we did all of this work to get to the same point as our 2 classes ago, where we had a nice diffuse light. But now we're set up very nicely to kind of start doing other kinds of objects, all by basically just changing the material properties. So what I set up as materials, so I set up a structure called material. So then, like, we're not using many of these right now, but we'll be using it in the next class. So right now we're mostly using base color and metallic. And you'll see the effect of it. So now you can change colors of object by changing the base color. You can see what effect light has on it. So we're set up in a very nice way for the next class to start generalizing things a bit more. But let's take a look at what we can do with this, what we have so far. So first thing we can try is see if it works still, if we move the light a little bit. So let's move the light a little bit down in the y direction. So that seems to work. Let's change the material base color to maybe more like reddish. There you go. So things are working fine. It looks like they're in a good place. So what I want to do then is stop here because we are at a good place to stop. We've done a lot, and I think we are getting to a place where it's a good renderer, except we have only one sphere, but it can render pretty much any kind of a diffuse surface. And next class, we'll add specular highlights and all the fancy stuff, and we'll put more objects around, so we'll get this reflection and other things. So it will be awesome. So let me go back to my presentation. So what you can do already probably is, so we'll continue building on the BRDF next time, unify everything, do some optimizations, because as we start adding more objects, things will get slow. So for homework, I want you to try varying the surface material by XY. So right now it's fixed. So do this experimentation where the surface is maybe a marble-like texture on it, and at the same time it is diffuse. So, or you can try just a varying color on the surface. And try animating the light. So I think the effects will be more obvious when you're animating the light, and light can kind of just move around in a circle a little bit. You can see the effects because we're not moving the camera, because our camera is kind of fixed at the origin. We can still move the light and kind of see the effects of changing light. So try this, and whoever does the best material, I will again give you a book courtesy of NVIDIA on ray tracing gems. So let's do something cool. Any questions in the last 1 minute we have? Are you guys excited? Like, I'm super excited. Like, this is we've come so far from when we started. So in the case when diffuse color comes from a texture, should we apply gamma to bring it to linear space from RGB? You don't have to do that. So I think Brent's code does that already for when it calculates diffuse. So it does the lin to mon thing. If not, then we'll add that. So that way we don't have to worry about that. I think the shader will take care of that, or the BRDF. Any other questions? All right, so if there are no more questions, let's stop here and continue on next week, where we will create some more materials. Now you've also found out the truth that I really don't have a piano, it's just a green screen. So, but we didn't crash and we didn't jitter. So I think that was one of the main causes, was the green screen is done with GL on the streaming platform you're using. So it was fighting with my shader toy. All right, I will see you all next week. Have a good weekend. Bye.
At SIGGRAPH 2020, more than 10,000 individuals from 95 countries gathered virtually to experience over 350 hours of content presented by more than 1,600 contributors. What resulted was pure SIGGRAPH. Robotic advances use subtractive fabrication techniques to carve foam and similar materials like an artist. Modeling and predictive computation creates a more robust and accurate time-stepping of nonlinear elastodynamics. New investigation into damage simulation could change the landscape of video and game effects, as well as surgical training. Novel healthcare technologies point toward new ways to transform and enhance lives. Research will help users to create reprogrammable multicolor textures made from a single material. AI-driven technology pushes the capabilities of crowd simulation. Award-winning animation showcases the latest in computer graphics. Real-time and gaming technology advancements transform interactive storytelling techniques and explore new applications of the technology. Evocative digital artwork uses machine learning to create visceral experiences. Now is the time to share your research, your innovations, and your creative inspiration. SIGGRAPH is your community, and we hope you'll share your work with SIGGRAPH 2021.